When we think about a chemical reaction, we usually picture it as a one-way street, right? Reactants turn into products. The end. But what if that's not the whole story? What if it's actually a never-ending cycle?
And that's really the core idea of what we call chemical equilibrium. It's not about a reaction just stopping. It's about it reaching this perfect dynamic balance. So let's break down how this constant push and pull really works. All right, first things first, let's bust a common myth. We often learn in chemistry that reactants turn completely into products. And look, that's a super useful simplification, but the reality is way more interesting and, well, dynamic than that. Here is the absolute key. Pretty much every chemical reaction is a two-way street. We show this with these special double arrows. It literally means that as your reactants are busy forming products, those very same products are turning right back into reactants at the exact same time.
Honestly, the best way to get your head around this is to just see it in action. So let's watch a classic reaction as it finds its perfect balancing act. So, we're going to start with a flask filled with this colorless gas, dinitrogen tetroxide, or N2O4 for short. The second we seal that flask, it immediately starts to break down in what we call the forward reaction. And there it is. You can see the change happening. That forward reaction, the N2O4 turning into two molecules of NO2, is going strong right now. And it turns out that NO2, nitrogen dioxide, is a brown gas. So the more of it we make, the browner the whole flask gets. But as more and more of that brown NO2 product starts to build up, something else starts to happen. We get a reverse reaction that kicks in. Those brown NO2 molecules start bumping into each other and recombining to form the original colorless N2O4 again. And then we hit this point. The color just stops changing. Now this is crucial. It does not mean the reactions have stopped. Oh, far from it. It means the system has reached equilibrium. For every molecule of N2O4 that breaks apart, a pair of NO2 molecules combines. The rates are perfectly balanced. This graph just nails what we saw with our eyes. The green line, our reactant, its concentration goes down. The purple line, our product, its concentration goes up. And then they both flatline. That flat part is equilibrium. The reaction isn't over. The net change is just zero. So this brings us to the official term for it, dynamic equilibrium. And I love that word, dynamic, because it reminds us that things are still happening. Think back to that tug of war. If both teams pull with the exact same force, the rope in the middle doesn't move. But are they still pulling? Oh yeah, they're pulling like crazy. That's exactly what's going on inside our flask. Okay, so if every reaction has this special balance point, you gotta wonder, how can we describe it? How can we, put a number on it? Well, that's where a really important number comes into play. It's called the equilibrium constant, and we just use a capital K to represent it. And it's actually a pretty simple ratio. All you do is take the concentration of your products and divide it by the concentration of your reactants after the system has reached equilibrium. This number, K, is like a unique fingerprint for a reaction at a given temperature. And the size of K tells you everything you need to know about where that balance point is. If K is a huge number, it means the top of that fraction, the products, must be way bigger than the bottom. So we say the equilibrium lies to the right, favoring products. And if K is a tiny little decimal, the opposite is true. You've got mostly reactants, and the equilibrium lies to the left. Okay, so K is the destination, right? It's that perfect equilibrium ratio. But what if you just mix a bunch of chemicals in a flask and you want to know, where are we right now? Are we at equilibrium yet? And if not, which way is this thing going to go? Well, for that, we use something called the reaction quotient, or Q. Now, here's the cool part. You calculate it the exact same way as K, products over reactants. But the difference is you can calculate Q at any moment in time. It's like taking a snapshot of the reaction's current status. This table really makes it crystal clear. I like to think of it like this. Q is your current GPS location. K is your final destination address. Your Q is constantly changing as the reaction drives along, but K is that fixed target you're trying to get to. So this is where the real power comes in. Once you compare your current location, Q, to your final destination, K, you can predict the future. Or, at least the future of your chemical reaction. And the logic here is actually super straightforward. If your current ratio, Q, is smaller than the target ratio, K, well, you need to make the top of the fraction bigger. You need more products. So the reaction has to move forward.
If Q is too big, you've overshot it. You've got too many products. The reaction has to shift in reverse. And if Q equals K, perfect, you're already there. You're at equilibrium. Let's put this to the test with a quick problem. Say we throw these 3 gases into a flask. We already know the destination. Our K value is 0.078. The big question is, which way does this reaction need to go to get there?
Okay, here's our game plan. It's a simple 4-step process. First, we'll write out the expression for Q, remember, products over reactants. Second, we'll quickly calculate the molarities, the concentrations for each gas. Then we just plug those numbers in and solve for Q. And finally, the moment of truth. We compare our Q to K.
So we plug everything in. Q equals the concentration of SO2 times the concentration of Cl2, which is 0.070 times 0.016, and we divide all of that by the concentration of our reactant, which is 0.100. And that gives us a Q value of 0.011. And just to remind ourselves, our destination, our equilibrium constant K, is 0.078. So let's do the final comparison. Our K is 0.078, but our Q right now is only 0.011. Clearly, K is greater than Q. Our current ratio is too small. To get to our destination, we have to increase the amount of products. The reaction must shift forward to reach equilibrium. And all of this leaves us with one last really powerful idea. Everything we've been talking about today, K, Q, the balance point, that's all in the realm of thermodynamics. It tells us where the reaction is going, but it tells us absolutely nothing about how fast it gets there. The speed of the journey is controlled by a whole different field of chemistry called kinetics, which just goes to show you that in chemistry, the 2 most important questions you can ask are always, where are we going and how fast are we going to get there?